Alright, my wonderful students, welcome to Chapter 3. I know that I've been a little bit delayed in posting this, and I'm really sorry. Nevertheless, I hope that it will be enjoyable. Before I begin, I want to just tell you a humorous story that sort of was an experience that I had in which I learned the importance of listening to instructions. Many years ago, back when I was in high school, I took an English class from a very phenomenal English teacher who also had a reputation as being very harsh. The rumor had been spread through our school that this particular teacher, because of her reputation as being very harsh teacher, but very good teacher, had her mailbox blown up by students using M80s and other fireworks numerous times. The rumor also existed that because of this, she had replaced it with a very strong cast iron steel mailbox or something like that. So this teacher gave us an assignment in which she instructed us to mark all of the particular parts of speech that she was focused on. I had not paid attention to the instructions properly and marked different parts of speech, and as a result ended up getting a very low grade on the assignment. The assignment wasn't that crucial for my overall grade in the semester. Nevertheless, I was kind of upset. So after class, I went and visited with her, and I explained to her that I hadn't heard the instructions properly, and according to the way I had heard the instructions, I had actually done it very well. She shook her head and said, "Mike, I'm really sorry to tell you this, but you're just going to have to take the grade that you earned." So in response to her reply, and being very disappointed, I calmly said to her, "My dear teacher, that is just fine, and I want you to know that I promise I will not blow up your mailbox this weekend." I realized that was probably a little bit too forward of me, but I don't know why. I was a little bit upset and wanted to test the waters. She looked at me and sharply replied, "I'd like to see you try. It's made of 3-inch thick steel." So I guess I learned that the rumors were true. After today's lecture, you guys should be able to do each of the following things. Name alkenes using the IUPAC naming system, including the cis-trans and easy naming conventions. Name alkenols, molecules that have both alkenes and alcohols in them and are also called enols. Explain what reaction mechanisms are and correctly draw the reaction mechanism of adding HX to an alkene. And describe the energy diagram for adding HX to an alkene, including the meaning of the terms intermediate and transition state. And lastly, identify a compound's degree of unsaturation. With that said, let's go ahead and get started. First of all, I want to teach you how to name alkenes. Step 1, name the parent chain. How do we name the parent chain? Well, we find the longest carbon chain that contains a double bond, and then we name the compound using its basic alkane name, such as methane, ethane, propane, butane, etc. But we replace the suffix "ane" with the suffix "ene." Step 2, we number the carbon atoms in the chain. Now, we always want to number in the direction that gives the double bond the lowest number. And 3, we write the full name, placing any substituents at the beginning of the name and the parent chain name at the end. Let's take a look at some examples. Give the IUPAC names for each of the following alkenes. Problem 1 is shown here. Now you'll note in this particular example, I could number the longest chain that contains the alkene going left to right or right to left. If I number it going left to right, then the double bond starts on carbon 3. If I number it going right to left, then the double bond also starts in carbon 3. So there's no difference. So how do I break the tie? Well, I do so by looking at the substituent. If I number going from right to left, then this substituent, this methyl group, is present on carbon 3. Thus, that is the direction I'm going to want to do it. Because it's a 6-carbon long chain, its parent name as an alkane would be hexane. Because it's an alkene, I change that to hexene, and because the double bond starts on carbon 3, I call it 3-hexene, or you can also call it hex-3-ene. This methyl group is found on carbon 3, thus the full name of it would be 3-methyl-3-hexene, or 3-methyl-hex-3-ene. Let's take a look at this example. It's a cycloalkene. Its parent name would be cyclohexane. In which direction do I number? Well, I want to give these two methyl substituents the lowest number, and in this particular case, it doesn't matter which direction I choose. Either direction will give me the substituents at the exact same location and the lowest possible number for my double bond, which is 1. Thus, this particular compound is called cyclohexene. I don't need to put a number for the double bond because the double bond begins at carbon 1. The substituents, methyls, are found on carbons 1 and 2. Thus, I will call it 1, 2 dimethylcyclohexene. Let's look at this example. You'll note that I could number going left to right or right to left. The direction in which I want to number in this particular case is going to be left to right because it gives me the lowest possible number for each of the carbons that begin my double bond. This is an interesting compound. It's 8 carbons long. If it were an alkane, it would be called octane. However, it's an alkene, so we would call it octene, except it's got 2 alkenes in it. So how do we name that? Well, we call it octadiene. And we also have to insert numbers in here to indicate where the alkenes begin. I have a double bond beginning at carbon 2 and one beginning at carbon 5. So I would call it 2, 5 octadiene, or I could call it octa 2, 5 diene. Where do the substituents appear? At 4 and 7. So I would call it, in its final name form, 4, 7 dimethyl 2, 5 octadiene. And here's one last example that I'll let you do on your own. I now want to teach to you the difference between cis and trans isomers of alkenes. Now, keeping in mind that double bonds cannot rotate as single bonds do, is there a difference between these two molecules? Look at them closely and even pause this and think about it before you go on. Now, you'll note that of course there's a difference. In this particular example, this methyl and this methyl are closer to each other, keeping in mind that this carbon-carbon double bond does not rotate, so these are frozen in place, unlike single bonds which can rotate freely. In this example B, this methyl and this methyl are further away from each other because one of them is staring at the other on opposite ends of the double bond. Which of these two alkenes do you think is more stable? Yeah, you guessed it. Obviously, it's going to be alkene B because the two larger groups, these two methyls, are further away from each other. As it turns out, compound A is called a cis molecule and compound B is called a trans molecule. In other words, alkenes that have two groups on them like this that are closer to each other on the same side of the double bond are called cis alkenes, and ones that are the opposite are called transalkenes. We'll talk more of that momentarily, but first I want you to remember from our last chapter that we also use the terms cis and trans to refer to the directionality of substituents on ringed compounds. So I want to emphasize that you should not confuse cis-trans of alkenes with cis-trans of cyclic compounds. Once again, remember that if we have a ring with two substituents, if the two substituents are going in the same direction, either both up or both down, then they are cis to each other and it's a cis ring. If they're going in opposite directions, then they're trans to each other. Here are a few examples. Cis 1,2-dichlorocyclohexane, cis 1,3-dichlorocyclopentane, and trans 1,3-dichlorocycloheptane. In contrast with alkenes, if you have two substituents that are on opposite sides of the carbon-carbon double bond, which are pointing in opposing directions, then they are cis to each other. If they're pointing in the same direction, then they're trans. So in this particular example, we would call this cis-2-butene, because these two methyls are on the same side of the double bond as each other. You could also call it cis-but-2-ene. And this molecule would be called trans-2-butene, or trans-but-2-ene. Either way is acceptable, because these two methyls are trans to each other. They're on opposing sides of the double bond. What about this example? Well, you'll note that this just has hydrogens. Hydrogens are not considered substituents, thus you cannot use the designation cis or trans. This example is just simply called 1-butene, or but-1-ene. Which brings us to a lecture question. Name the following alkenes, including cis or trans designation. Let's look at this first one. What in the world would I name it? Well, obviously I'm going to count the carbons in the longest chain in the direction that gives me the smallest number to my alkene. That ends up being right to left. 1, 2, 3, 4, 5, 6. So this is going to be a hexene, and if I number going right to left, the double bond starts on carbon 2, so it's going to be a 2-hexene. Is it cis or trans? To determine that, I just draw a dotted line down the middle of the double bond and I ask myself, are the two hydrogens on the same side of the double bond as each other or on opposite sides? If they're on the same side, then all of the business stuff is also on the same side and it is a cis alkene. If they're on opposite sides, then it's a trans alkene. And which turns out to be the case in this particular example? Yeah, you guessed it. This is a cis hexene. And of course I could point out that it is a 4,5 dimethyl cis-2-hexene. Let's look at this example. In which direction do I number? Well, once again, I'm going to number right to left because that gives me the lowest number where the alkene is, and this is going to end up being a 3-heptene. Is it cis or trans? I draw a dotted line right down the middle of the double bond and ask myself, which sides are the hydrogens on relative to each other? Are they on opposing sides or the same side? These are on opposing sides, thus this is a trans 3-heptene. Now, how do you think we name these? I want you to look at them for a moment and ask yourselves, is this cis or trans? Let's take a closer look by drawing a dashed line down the middle of it. Are the two hydrogens on the same side or opposite sides of each other? On this particular example, there aren't two hydrogens. So can I say this is a cis or a trans molecule? And if I do, isn't it kind of confusing? Because am I talking about the chlorine being trans to this methyl, or this methyl here being cis to this methyl? Or the chlorine being cis to the methyl? Am I talking about the two methyls or the chlorine and the methyl? Or the chlorine and the hydrogen, or the I hope you can sort of see this gets kind of confusing. Similarly, looking at this example, if I use the designation cis or trans, what am I talking about? Am I talking about this bromine being cis to the methyl? Or this ethyl being trans to the methyl? Or this methyl being cis to the bromine, or the bromine being trans to the hydrogen? Or what in the world am I talking about? Well, I hope you can see that using cis and trans to name alkenes only works if you have one hydrogen on each of the two alkene carbons. Now, if you don't, if in other words you have other substituents, then you have to use a different convention, which is called the EZ naming convention. I'll explain that to you now. Here's how it works. You basically draw a dashed line down the middle of your carbon-carbon double bond, and then you look to the left of it and decide who is higher priority, and you put a check mark next to them. You look to the right of it and decide who is higher priority, and you put a check mark next to them. If the two higher priority guys are on opposite sides of each other, as in this case, then it is called an E double bond. If they're on the same side as each other, it's called a Z double bond. Here's an easy way to remember that. Z is on the same side, and E are on opposite sides. Once again, if the two highest priority guys are on opposite sides of each other, it is an E alkane. If they're on the same side as each other, then it is a Z alkane. And that's the way it works. Now you might be wondering, what in the world, Mike, do you mean when you say higher priority? Let me show you the rules. To determine a substituent's priority, we have to remember that one higher atomic number equals highest priority. Now, if there is a tie, then you keep going out one atom at a time until you break the tie. Multiple bonded atoms are considered to be like the same number of single bonded atoms. For example, if I've got this thing coming off of an alkene, it's a carbon double bonded to an oxygen, we can consider it for the purpose of determining if it's higher or lower priority as being like a carbon that's single bonded to one oxygen and single bonded to another, which is single bonded to a carbon. Here are some other examples. If I had an alkene down here, and coming off of it was another alkene as a substituent, this carbon-carbon double bond would be counted for priority purposes as if this pink carbon were single bonded to one carbon in green, single bonded to another carbon in green, which is in turn bonded back to a carbon in pink. If I had this carbon-carbon triple bond coming off of our alkene, it would be as if this carbon were bonded to three separate green carbons and this green carbon were bonded to three separate pink carbons. That is how I would count it for priority purposes. Let's take a look at some examples. In this example, I'm asked to determine if this is E or Z. How in the world do I do that? What I do is I draw a dashed line right down the carbon-carbon double bond. And now I'm going to look at the two substituents on the left. I've got a carbon and a carbon. Which one has a higher atomic number, a carbon or a carbon? They're the same, so they tie. So now I move out one atom to a hydrogen, and this carbon is bonded to another carbon. Which has a higher atomic number, carbon or hydrogen? Carbon does. So this guy down here is the higher priority substituent on the left side of the alkene. Now on the right side of the alkene, I've got a carbon and a chlorine. Who has a higher atomic number? The chlorine does. So this guy is the higher priority substituent on the right side of the alkene. I've got my higher priority substituent here and my higher priority substituent down here. These two guys are on the same side of the alkene, and therefore this is a Z alkene. Let's look at this example. How do I determine who has the highest priority? I draw my dashed line down here, and I go out looking at the two substituents on the left side of the dashed line. I've got a hydrogen and a carbon. Who has a higher atomic number? The carbon does. So this methyl group is the higher priority substituent between these two. On the right side of my carbon-carbon double bond, I've got a carbon that's triple bonded to a nitrogen and a carbon that's single bonded to a nitrogen. Who has higher priority? Well, if I keep going out, the tie gets broken out here. This guy's the higher priority. So I've got highest priority guy down here on the left and up here on the right. Are they on the same side or opposite sides of the double bond? Well, they're on opposite sides. And remember, if you're on opposite or opposite sides of each other, you are an E alkene. So this is indeed an E alkene. How do we name molecules that have both a carbon-carbon double bond in them and an alcohol somewhere else in them? So it turns out molecules that have both alkenes and alcohols in them are called alkenols, or sometimes just called enols. They basically come up with that name by combining the words alcohol and alkene and squishing them together to make one word, alkenol, or enol, simply. Now these are named by combining elements of the steps for naming alcohols, which we discussed in our previous chapter, with the steps for naming alkenes that we just covered. Because the alcohol component has higher priority than the alkene component, when we name an alkenol or an enol, we have to number the parent chain that gives the lowest number to the OH, not the double bond. Let's take a look at some examples. How do we name the following enols that we've just taken a look at? Here's how we do it. First of all, we decide which direction I'm going to number in. In this particular example, I'm going to number starting at this carbon right here, going right to left. 1, 2, 3, 4, 5. Because it has an alkene in it, and it has 5 carbons in it, this is going to be a pentene. The alcohol is coming off of the pentene at carbon 1, thus it is a pentenol. This particular example, my alcohol is coming off of carbon 1, and my carbon-carbon double bond begins at carbon 3. Therefore, I'm going to call it pent-3-ene-1-ol. Pent-3-ene-1-ol. Off of carbon 3, I've got the chlorine, and off of carbon 4, I've got the methyl. So it would be 3-chloro, 4-methyl, pent-3-ene-1-ol. In this particular example, I could number going right to left, 1, 2, 3, 4, 5, 6. Or I could number going left to right, 1, 2, 3, 4, 5, 6. If I number going right to left, I get a smaller number for my double bond. However, the double bond is lower in priority than the alcohol, so I need to number going left to right. 1, 2, 3, 4, 5, 6 is a hexene, and with the alcohol on it, it's a hexenol. Thus, because this particular carbon-carbon double bond occurs at carbon 4, I would call it hex-4-ene-1-ol. I've got an ethyl coming off of carbon 4, so it would be called in end 4-ethyl hex-4-ene-1-ol. Alright, so that brings us to the end of this lecture. Please tune in to the second half of our Chapter 3 discussion, in which I will teach you guys about reaction mechanisms and energy diagrams. Until then, have an enjoyable day.